Our next chapter is a plane stress. Okay, this is very simple chapter and easy to score the mark. Okay, even though the structure looks very complicated, but the analysis and finding the stress is very simple in this. You should not miss any question from this. And apart from that, learning about this is very much important as a mechanical engineer. Why? Because these plane stress structures you will see everywhere. For example, your workshop buildings, or whenever you are having very huge support. Huge support means huge tent with, so how will it stand? You need to have some structure there. Okay, that structure is nothing but the plane stress structure. Okay, why it is called as the plane means it is a 2D, right? For example, here if you look at this, what is happening here? See, this is the top cover. Okay, this is the top cover, and this is the beam, and this beam means this is the column, and this is another column, and here in between the top cover and the columns we have this structure. Okay, so here this structure, instead of having only the triangular shape, we have some other slenders are slender, slender, slender rod, or simply we can say that some rods whose weight is negligible here in this case. Okay, we neglect the weight of these rods are negligible. Okay, we kept like this so that what is happening, the load exerted by this top cover is taken by this stress structure. Okay, and here if you take this structure, and if I draw here like this, so what is happening, these are the different rods, and how these different rods are connected with each other. All these rods are connected with each other with revolute joints like this. Okay, these are revolute joints. These are connected with revolute joints. Okay, see, for example, here we have only two rods which are coming together, so that we are joining them with a pin or a revolute joint. And in case of three rods meeting at one place, how you join those three? Okay, generally we join something like on a plate. So here one rod, another rod is like this, and the third rod will be like this. Okay, so all these rods are connected to a plate with a revolute joint. That is how we will do. But we assume that while solving the problem, we assume that all the three joints are at one place. Okay, instead of joining at a plate here. Okay, let's come back to the name of the chapter. What is that? The plane stress. Okay, so why it is called as the plane stress? All the forces and as well as the stresses produced or internal reaction produced because of the external forces are in the same plane. For example, here some force is produced at the point A. Let's assume this is the B, C, D, E. Okay, and then F. So here if I apply the point load at A, then what is happening? All these slenders are, all these rods are on the same plane, and whatever stresses produced in these rods are also in the same plane. That is why even the reactionary forces. What are the reactionary forces? Let's assume this is the point C and this is the point B. So here the reactionary force RC and then RB. Okay, even the reactionary forces, the applied force, and the internal reactions are the stresses produced in these slender rods, everything in the same plane. That is why these are called as the plane stresses. Okay, so for our exam, only plane stresses are important here. Okay, and what are other assumptions actually here? Even see, these you can see very much in the bridges also. Okay, as shown in the starting we have shown some pictures. So whenever you have railway bridge side may we have the structures like this. Okay, for example, see, you might have observed some more structures like this. Okay. Okay, so why these structures are kept like this, to give some extra strength. These type of structures also called as in the theory of machines, next chapter we will see, these type of structures are called as the superstructures. The degree of freedom, the structure is called, when can we say the structure? When the degree of freedom is 0. Okay, when the degree of freedom is becoming less than the 0, then it is called as the superstructure. Okay, already it is not moving. Our main idea is whenever you take this structure, it should not move. Okay, it should not have any independent motion. Okay, then you already achieved that objective of not having any independent movement. Then why again you are further restricting, because it will give the extra strength to the structure. That we will see the next chapter. So here before we go further, okay, so always in a stress, what is the first assumption that we have seen? All rods joining at one junction. Okay, even though they are connected on the plate. And next important assumption is all forces applied, okay, at junctions only. Junctions are joint, otherwise I will call it as a joint. That is much more appropriate. Okay, joints. So what is the meaning of that? For example, here if I take this is the stress structure. Here in this structure, what are the joints? This is one joint, this is another joint. So these are the joints. Okay, these are the joints. And what are the rods? These are the rods here. Okay, these are the rods. And here, whenever the force analysis is carried out for this, always we need to assume that the forces are applied only at the junction. Junction means this joint. Okay, it can be applied here F1, or it could be applied here F2, or it could be applied here F3, like this. Okay, that is the meaning of this assumption. And here what happens, some of the rods may subjected to the tension and some of the rods may subjected to the compression. Okay, so the rod which is subjected to the tension is called as the tie member. Okay, it is called as the tie member. Even if you don't know this terminology, no need to worry. And the rod whichever is subjected to the compression is called as the the compression is called as the strut. S-T-R-U-T, strut member. Okay, it is a tie member and a strut member. Okay, and after this we will see the types of frames. So what is the meaning of the types of frames here? These frames are based on how many joints are there and how many members are there. Member mean how many rods are there. Okay, based on that these are divided into 3. What are those 3? Perfect stress, collapsible stress, and redundant stress. The name itself is indicating. Okay, so what is the meaning of that? So here first one is a perfect, second one is a collapsible, okay, and what is the third one? The third one is a redundant. So third one is the redundant. So what is the difference between all these three? Okay, for example, what is the meaning of this collapsible stress? Collapsible stress, meaning of this collapsible stress is, the stress is not a structure, that means it will move. Okay, for example, here if I take one structure like this, okay, and if I join all these joints with the revolute joints, then what happen? If I apply some force, it may move, like this. It is a, not a structure here. That means what is the meaning of this structure? Structure meaning, it is not having any independent motion. That means its degree of freedom is 0. But whereas here what happened? Otherwise, if I apply some force like this horizontal force, then automatically it will move like this. Okay. So instead of this, if I take a structure like this, okay, triangular structure or a truss, here in this case also all these joints are connected by using the revolute joints. Here in this case, whether I apply the horizontal or the vertical force here, is there any motion between these two? Of course there is no motion. Okay. In the same way here, for example, if I keep some extra rod like this joining this corner revolute joints, in that case is there any motion in this case? There is no motion in this case. Okay. So now by addition of one extra member, the collapsible stress is converted into the perfect stress. Okay, and here now it became a perfect stress, and again if I add one more rod here, then what happened? It converted or it changed from the perfect stress to the redundant stress here. Okay, why redundant? Whether you keep this rod or remove, this is not having any motion. Okay, if I remove this rod or this rod, okay, either of these two if I remove, then there is no change in the structure movement. Okay, so whatever extra link we added, it is a redundant. That means it is not adding any extra functionality. Okay, then why we are adding? In some of the cases intentionally we add that, even though it is not changing its functionality, but functionality means in terms of the motion of this truss, it is giving extra strength to this truss. Okay, it is giving extra strength. Okay, so in this simple case, okay, it is by observation it is easy to understand. But in actual scenario, in the examination, if some stress is given to you and then if you are asked to find out the nature of this stress, then how will you do that? In that case, we need to use this formula. What is that? M equal to 2j minus 3. Okay, where M equal to, otherwise I will write N. N equal to 2j minus 3, where n equal to number of members. Number of members means it is a number of rods here. Okay, and then j equal to number of joints here. Number of joints here. Okay, so for example, if I take, we will take some examples here. Same example I will take. What is that? This rectangular truss. So here this is a rectangular truss here. Okay, here number of rods 1 2 3 4. So number of rods are 4 here, and the number of joints are how many? 1 2 3 4. So here j will become 4 here. So if I apply this formula, n equal to 2j minus 3. 2 into j is how much? 2 into j is 8. 2 into 4 minus 3, how much? This will be 8 minus 3 means 5 here. Okay, and here n value is how much? N is 4. So that means here 4 not equal to 5, right? 4 is not equal to 5. So this condition is not satisfying. And here what is happening? See, whenever that condition satisfies, where n equal to 2j minus 3, if this condition satisfies, then it is called as the perfect stress. Okay, here in this case that condition is not satisfied, and here moreover what is happening, n is less than the 2j minus 3. In such cases it is called as the collapsible stress. Okay, that is what happening here, right? If I apply some horizontal force like this, then it is having some motion and it will collapse. It is no longer a structure here. Okay, and now here I will apply, see, I will add some extra link like this. I will add some more extra link like this. Okay, when I add some extra link like this, then here what is happening, n equal to how many number of rods are there, 1 2 3 4 5 rods, and then what is the j here, j is 1 2 3 4. J, even though you add one extra rod, the number of joints are not changing. Why? Because you are connecting this extra rod to the existing joints. Okay, so here j equal to how many, 4 here. And here you might be having some doubt, what is that? For example, in case of theory of machines, when we are calculating the degree of freedom for the mechanisms, whenever you have 3 links or the 3 rods joining connected or joining at one place, then the number of joints at that point is considered as the how much, j, it is nothing but j minus 1. J minus 1 in the sense, here there are 3 rods, so 3 minus 1, 3 minus 1, so here j will become how much, otherwise this formula is L minus 1. Okay, L minus 1, so L is 3 rods, so 3 minus 1 means 2, so j value should be taken 2 here, and here also j value should be taken 2, so 2 plus 2 is 4, 5 and 6. So instead of this formula, if we are calculating the degree of freedom in case of the theory of machines, then how many joints you need to count here, 6. Okay, don't confuse with that formula. Okay, here we are not going to use count like that. Here we are simply counting only the number of joints in the struss here. So how many joints are here? Only 4 joints. So if I apply the formula, 5 equal to 2 into 4 minus 3, so 8 minus 3 means 5. So 5 equal to 5, so it became perfect structure. It is a perfect structure, but whereas this became collapsible structure. Collapsible structure. Why? Because here n is less than the 2j minus 3. And what's about this redundant structure? In case of the redundant structure or the stress, n is greater than the 2j minus 3. Okay, that means here we are using the more number of links than the required one to make it a perfect stress. So if I take the same example here, okay, this is the rectangular stress here like this, and to make it a perfect stress, I am adding one extra diagonal one, and again I will add one more extra one. Okay, so here number of members become how many, 1 2 3 4 and 2 diagonal rods here. Okay, so 4 plus 2 is 6. And what's about the j, number of joint, 1 2 3 4, number of joint is 4 here. So we need to see from this whether it is satisfying this or not. So n equal to how much, 6, and on the right hand side how much is there, right hand side 2 into 4 minus 3, that is 5 only. Okay, so here 6 is greater than the 5, so it is satisfying this equation, this condition, so it became the redundant. Okay, so that is how we need to compare whether it is a perfect structure or a collapsible structure or the redundant structure. Okay, now we will see whether these stresses are perfect, collapsible or the redundant. For example, here this is a triangular and n equal to how much? N equal to 3, and then j equal to 3 here, 1 2 3. So 3 equal to, whether it is becoming or not, 2 into 3 minus 3, so 3 equal to 3. So it is a perfect struss. It is a perfect struss. And what's about this? How many are there? See, wherever joint is there, the rod between two joints is considered as the one member. So here n equal to how many? 1 2 3 4 and then 5. So n equal to 5 here, and then j equal to how much? 1 2 3 4. So j equal to 4. So here formula n equal to 2j minus 3. So 5 equal to 2 into j is how much? 4 minus 3. So how much it became? 5. So this is also perfect. So this is also perfect. And what's about this? So 1 2 3 4 5 6 7 8 9. So n equal to how much? 9 here. And then what's about j? J equal to how many? 1 2 3 4 5 6. J equal to 6 here. So 9 equal to 2 into 6 minus 3. So 12 minus 3 equal to 9 here. 9 equal to 9. So it will become perfect. Perfect structure. Okay. Because these type of examples we are going to see, that is why everything is coming to perfect. In this chapter, whatever structures we are going to deal, everything is a perfect struss here. Okay. And here in this case, what is the n here? 1 2 3 4 5 6 7 8 and then 9. Okay. So n equal to 9. And then what's about the j? J equal to 1 2 3 4 5 6. So 6. Again the same formula. So 9 equal to 9. This is also perfect struss here. Okay, this is how we need to see. And generally the problems which are given here in the examination, everything is a perfect struss. Okay, if it is not, then the force values changes. Okay.